All right, welcome to the Explainer. Have you ever really stopped to think about how a simple keypad, with numbers 0 through 9, can talk to a microcontroller that only gets ones and zeros? Well, today, we're going to pull back the curtain on some really clever digital codes that make that whole conversation possible. They're the bridge between our world and the binary brain of a computer.
So here's the basic problem, right? The brain of any project, the microcontroller, it's a native speaker of binary. That's all it knows. But the things we use to talk to it, keypads, 7-segment displays, they all speak in our decimal system. So, how do we translate? How do we make sure that when you press the number 9, the chip doesn't just see a bunch of meaningless bits and get confused?
Well, the answer is a special language that was built just for this job. It's called Binary Coded Decimal, or BCD for short. And you can think of it as the perfect interpreter, something that lets our electronics see numbers the same way we do.
The real genius of BCD is just how simple it is. Instead of taking a big number, let's say 123, and converting it into one long, messy binary string, BCD just breaks it down. It takes the 1, translates it. Then it takes the 2, translates that. Then the 3. Each one gets its own little 4-bit binary group. And this digit-by-digit way of doing things is absolutely perfect for stuff like digital clocks or voltmeters, where each number on that display is its own little component.
So this is basically the cheat sheet. It's the translation key. Every decimal digit from 0 all the way up to 9 gets its own unique 4-bit code. It's a straight one-to-one swap. Now, what's really important to see here is that for any number up to 9, the BCD code is exactly the same as regular old binary. The real magic, the difference, happens when we need to show numbers that are bigger than 9. Let's use the number 12 to really see how this works. A computer's processor, which is built for raw number crunching, sees 12 as a single binary value, 1100. Simple. But for something like a display, BCD treats the 1 and the 2 like they're two separate things. So the 1 becomes 0001 and the 2 becomes 0010. Yeah, it takes up a little more space, but that separation is exactly what makes it so incredibly easy to just shoot each digit to its correct spot on a screen.
Now, when it comes to storing this BCD data, you've got a couple of options. The first way is what we call unpacked BCD. And with this method, each little 4-bit BCD digit gets a whole 8-bit byte all to itself. So for the number 91, the 9, which is 1001, gets its own byte, and the 1001 gets another. The extra 4 bits in each of those bytes, they're just filled with zeros. It works, it's simple, but man, it's inefficient. You're basically wasting half your storage space.
A much smarter approach is packed BCD. This is where we really start being efficient. We take those 2 BCD digits for the number 91 and we pack them both into a single 8-bit byte. The 1001 for our 9 goes into the first half, what we call a nibble, and the 0001 for the 1 goes right into the second half. See that? No wasted space at all. So much better. So BCD is perfect for our keypads and displays. But what happens when our digital system needs to read something from a physical object that's moving? Like when you turn a volume knob. A normal binary system can get really confused by those tiny, imperfect movements, and that leads to all sorts of glitches. This kind of problem, it needs a totally different kind of code.
And this is where gray code comes in to save the day. Its superpower, its whole reason for being, is that between any two numbers right next to each other, only a single bit ever changes. Just one. Think about normal binary. We're going from a 7, 0111, to an 8, 1000, makes all 4 bits flip at the same time. Gray code avoids that mess. This also means it's a non-weighted code. The positions don't stand for a power of 2, which is the key to making it so stable.
Just like the slide says, the whole point is that adjacent numbers only differ by one single digit. And think about why that is so important. When a mechanical sensor is trying to read a binary number changing from 7 to 8, all 4 bits are flipping at once. For just a tiny fraction of a second, the sensor might see a totally crazy value, like all zeros or all ones. That's a glitch. Gray code completely gets rid of that possibility. Since only one bit is changing, there's no weird in-between state. It's either the old number or it's the new number. Clean, simple, no errors. Okay, so how do we actually get from binary to gray code? It's actually a pretty straightforward process. First, you take the most significant bit, the one all the way on the left, and you just bring it straight down. It never changes. For all the other bits, you use a simple logic operation called XOR. You just look at the bit in the original binary number and the one to its left. If those 2 bits are different, your result is a 1. If they're the same, the result is a 0. And you just keep doing that all the way down the line.
Now, going back from gray code to binary is just as logical, but with a little twist. Again, that first bit just comes straight down, no change. But after that, it's kind of like a chain reaction. You XOR the binary bit you just figured out with the next bit over in the gray code. That gives you your next binary bit. Then you use that result with the next gray code bit, and so on. It's this cool cascading effect where each answer helps you get the next one.
Okay, so we've got a code for displays and we've got a code for sensors, but there's one piece still missing from our puzzle: doing math. I mean, you can do arithmetic with standard BCD, but the circuits you need to build get really complicated, especially when you have to do subtraction. So to make things a whole lot simpler, engineers came up with a very clever variation.
And that variation is the Excess-3 code. The logic is, believe it or not, right there in the name. You take each decimal digit, you add 3 to it, and then you find the binary code for that new number. So the number 0 becomes the binary for 3, 1 becomes the binary for 4, and you just keep going. Now, why on earth would we do that? Well, it creates what's called a self-complementing code. And all that fancy term means is that to do subtraction, all you have to do is flip all the bits, change the 1s to 0s and 0s to 1s. This makes designing the circuits for math way simpler.
Making an Excess-3 code is dead simple. Let's just take the number 24. First, you split the digits apart. You've got a 2 and a 4. Then, you just add 3 to each of them. So, 2 plus 3 is 5, and 4 plus 3 is 7. For the last step, you just convert those new numbers, 5 and 7, into their normal 4-bit binary codes. So 5 is 0101, and 7 is 0111. And that's it. The Excess-3 code for 24 is 0101, 0111. Easy.
So when you look at all of this, what we've really seen are 3 different solutions for 3 totally different kinds of problems. We've got BCD for our displays, gray code for our sensors, and Excess-3 to help with arithmetic. And this really gets us to the most important thing to remember from all of this.
And that is, there is no single best code out there. It just doesn't exist. There is only the right tool for the right job. When you're at your electronics bench, you're going to reach for BCD when you need to talk to a person. You'll grab gray code when you need to read a moving part without any glitches. And you'll use Excess-3 when you need to make your math circuits simple and efficient. Knowing which tool to grab and when, well, that's what makes you a smart engineer, and it'll save you a ton of headaches in the real world. These codes really are the unsung heroes of the digital world. They're the translators working behind the scenes that let our world connect seamlessly with the binary world of computers. I hope you'll join us next time on The Explainer, because we're going to expand our number toolkit even more. We'll learn all about octal arithmetics and hexadecimal arithmetics. I'll see you then.